So welcome to part 3 of our extra lecture on the Jordan form. Just to kind of recap of where we are, okay, and I really find that this picture is helpful, so I hope you do too, is we've started with a basis for the big space. We use that to find a basis for this space, and then we use this basis to pull it back up to give us a basis for this space, and then we're pulling that basis back up to give us a different basis for the generalized eigenspace. And at the end of the day, where we left off at the last video is we had these three vectors right here is the basis of my generalized eigenspace. Okay, and notice that it has the property that if we take the first vector and we multiply it by the matrix, it bumps to the second matrix, and if we took the original matrix and we multiplied it squared, it bumps down to the last matrix here. Right, so our basis, let's see if I left it. So our basis has the form v, v1, mt minus 20I v1, and mt minus 20I v1, that operator squared times v1. And this is exactly kind of the form that we wanted it to have because this is a nilpotent operator on the generalized space, and we were looking for a basis of this particular form, where it's a vector, the operator applied to it, a power of the operator applied to it, to some point where it vanishes. And so this is actually the required basis for it, right? And if we combine this basis with the basis that we had for the generalized eigenspace of 10, we're actually in a good shape here, because this is exactly what we wanted. And let me just find it on my notes. I kind of lost it. There we go. Repeat the basis. So we had 1, 1, 1, negative 1. And then we had, sorry, I want to put it in a particular order. So I'm putting it in the wrong order, because the order is important. Actually, I did have it in the right order. 1, 1, 1, negative 1. And this is 1/5, 0, 1/5, and 0. And then we had 17 300ths, 1/30th, 2/30th, and 0. So with the property such that with respect to this basis, the matrix here, associated matrix, looks like 10, 0, 0, 0, 0, 20, 0, 0, 0, 1, 20, 0, and 0, 0, 1, 20. And this is, as we noticed before, here are the Jordan blocks. We have upper triangular matrices, okay, on the diagonal, and each upper triangular matrix has just diagonal entries and some ones in the entries above it. So this hopefully gives you a rough overview of how the procedure works. Okay, and let me just kind of wrap up here of just giving you the broad strokes of the general strategy. Okay, so hopefully I'm not covering everything up with my face. When you look inside of the proof of theorem 8.55, okay, there is an algorithm hiding inside of there, but it's not presented as an algorithm. And hopefully what I've done here is kind of try to pull the algorithm out from the proof. And really the strategy works as follows. You're taking a basis for the range at the D step. Okay, so you're looking at a basis for the range, that step. And what you're doing is for each element in the range, you're solving this equation. Okay, so you're solving it for all I. And what you want to do then is, now you're taking the original elements you had. I changed my index, so let me fix that here. And for each of these U1 to UT, you've solved this equation. So you get a W1 that goes to each of these guys. So now you kind of doubled the number of things. All of these things are inside of the D minus 1 power of the range of this operator raised to the D minus 1th power. Now, find the linear independent elements. You actually don't need to do this. Within the proof of Axler's, he actually shows that when you do this, these elements are actually linearly independent. Okay. Then what you need to do is you need to take those elements, and let me put the right index here, and you have to extend, you may have to extend it to a basis, okay, because the range might actually be bigger than the things that you found at the previous step. Okay, so you extend it to a basis, and you can just do this any way that you want, that we learned in the class. And then what you want to make sure is you want to make sure that each of these zi's, when you apply this operator one time, it gets sent to 0. And you can do this because each zi, when you apply the, oh, this should not be n, it should be the operator t minus lambda I times zi. And oh, here, just to make it easier, then you let n equal the operator t minus lambda I. And when you apply the operator here, it bumps into the range of t minus I to the d. Because this is a basis of the range, you can write the image in terms of this element right here. But you also know that each of these ui's equals n times wi. Okay, and then because you have a linear map, n is a linear map, you can write n is equal to a1 w1 up to at wt. So what you can do is you can replace each basis element with zi minus a1 times w1 up to at wt. So you replace each of these guys, and what you still have a basis after you do this. Okay, so there's lots of stuff going on in the background here, and that's kind of why we're kind of didn't go through all the details, but this is actually what's happening there in the background is you're replacing, you extend the basis, you replace it with a better basis such that each of these things get mapped to 0. And then you have the property, as I said, is that each of these new basis elements get sent to 0. Okay, so at the end of the day, all right, you're having a nice basis for the range of t minus I to the d minus 1, and then you go back and feed it into the machine again and you repeat. Okay, so you're building your bases as you go up one by one. Okay. So as you can see just from this description, and this isn't even super formal, that it's kind of hard to, it's not, the mechanics aren't hard, okay, of actually solving some of these things, but it's just a very time-consuming process in order to find all of these things. But that's what the Jordan form is, okay, how, in a specific example. Kind of the takeaway, though, is that when you have an operator coming from a vector space, complex vector space, you can actually always find a basis that you can write it in this form. So I hope you found this extra supplementary bonus edition of Lecture 25 helpful. As I mentioned at the beginning, it's unlikely that on any test or midterm that I would give you a question to compute the Jordan form. Okay, but I may give you partial information and you can try to see what you can do with that information. Okay, I hope this helped. We're only doing the 3 parts for today because it's supplemental. Have a great day.